This is video 6 in a series on creating a Fortnite locked chest that uses the WS2812B LED as a display. In this video, we will set up the MPLABX project necessary to drive this display and develop some sample code. Then we'll take current measurements to see how much current the WS2812B pulls with different colors at different intensities. So let's create a project that can drive our WS2812B LED. In MPLABX, we'll go to New Project, Microchip Embedded, Standalone Project. We'll use the PIC 24FJ256GA702. We'll use the PIC Kit 4 that I use for debugging, and the XC16 compiler. We will call this project LED Demo Video and say Finish. Now we'll go to Tools, Embedded, Microchip Code Configurator, and we'll use that to set up our chip. And we'll save my config. Now we're going to use the FRC oscillator. Let's enable the PLL. And we want the 4:1 prescaler, which multiplies this up. That gives us a 32 megahertz oscillator, which is good. So that looks good for our setup. Now, we're going to need a SPI peripheral. We'll use this one, SPI 1. And later in this project, we're also going to want DMA. So let's add DMA. For SPI 1, master, that's good. Communication with 8-bit, we wanted 10, but 10 isn't an option. 16 is an option, so we'll use that one and then modify it by hand later. SPI clock frequency, 8 megahertz. In a prior video, I said I thought we needed to use the reference clock in order to get there. That's actually not true. When I was doing my investigation, I had one of my clock divisors off, which made it look like you had to do that. You can get the 8 megahertz clock on the SPI directly from the 32 megahertz system clock. Clock polarity idle low, that's what we want. Clock edge idle to high. SPI mode 1, good. Now we need to connect up the SPI pins to the outside. So we said previously we were going to use pin 26 for SDO. You can see the schematic we had last time. Previously there was a reference clock down there we took out. And just for reference, we'll put the SPI clock on the pin 25, even though we're not actually using it to drive the LED. So there's pin 25. That looks good. Let's take a look at the DMA. The DMA, for the DMA, we're going to use the DMA to automatically transfer data from an array in memory into the SPI at some point. So we're going to say, okay, let's enable channel 0. We don't want to enable reload. We want to set those up manually. Transfer mode one shot, that's good. That's what we want to have happen. Trigger source, we will set up for the SPI 1. Where's the one we want? SPI 1 general? No. SPI 1 for the SPI 1 transmit interrupt. So that when the SPI 1 says, oh, okay, my buffer is not full anymore, the DMA will automatically load the next result. The source code mode we want to increment because we're going to be moving through a manually created array. The destination, we always want it to point to the SPI input buffer. So the rest of these we'll leave alone. Some of the stuff we'll be setting up manually. So let's go ahead and hit generate. That's good. Go to projects. If we go to source files, first thing we're going to want to do is just do a sanity check on our SPI bus. So let's go into SPI, take a look at the code they generated for us. Turns out there's a function in here that lets you do a single word transfer. That looks good to me. So let's go back to the main, and we will just continuously transfer data. We'll have some alternating bits at the beginning, followed by, how about 4 high bits and 3 off bits and 1 on bit. Let's build that. It's loading the code. And this is what we get on the scope. Let's take a look. And see what kind of bit lengths we're getting. If we use the cursor, actually we got one that fell from here to here. That looks about right. The cursor is 115 nanoseconds, which is very close to the 125 that we want. Could be a little bit of measurement error. Also, if we look at the width that we're seeing on channel 2, we're seeing a pulse width of 125 nanoseconds, which is exactly what we want to see. So we've got our on, off, on from the 0x55, followed by the 4 bits that we have high here, followed by the 1 final bit that we got here. Let's move the position just a little bit and make sure that they line up just the way that we want. And yes, we can see on the purple lines that those line up very well with our bit time, which is 125 nanoseconds. Now, let's see what we can do to actually generate some code. I'm going to close this particular file and reopen one that I finished later. Oh, let's do one more thing before we do that. We can see here that we're getting a full 16-bit transfer. We don't want that. Let's go into the SPI code. One of the things that you have to understand is that in most cases, code generators just get you started. It doesn't necessarily get you to where you want to be. So you should get comfortable with what all the registers do, what they're really for. So I want, instead of a 16-bit transfer, I only want a 10-bit transfer. And it turns out that the number of bits you want minus 1 is what you put into the SPI1 con2 low register. So let's rebuild that now and see what we get on the scope. Up at the top in the yellow, we can see the clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we can see here is we've got a good start. If we zoom out, we really wanted a controlled high and low time. We're getting a good bit count here, but there's a significant delay for us in how long it takes for us to reload the register and get it to send out some more data. We can mitigate this to some degree by using the queued capability of the hardware, but we're not going to get around that altogether because we're still reliant on the processor to come periodically around and reload the register. Even in this tight loop, we can see that it's not quite fast enough. The only thing we're doing here is putting data into this. Now we've got some overhead to go around the loop and to make the function call to pass the parameters. Essentially, it just takes too many instructions compared to how long it takes to send out a SPI message. So the solution for that is for us to use DMA. The DMA will effectively move data from out of an array that we create into the registers as fast as the registers need it. I'm going to close this particular project right now and open another one that I created. In here, you'll find a file. This project is available on my website at broadwell.consulting. If we look in here, there's a file, WS2812B demo, that I created. I put all of the WS2812 specific stuff in this file, put it under an MIT license so that you guys can use it as long as you attribute where it came from. If we take a look at the SPI bits that we want to send, we're going to want to load in bits 10 at a time. when we looked last time at our bit times, and we want to use the 8 megahertz column, we decided that a high needs to be 6 bits at 125 nanoseconds, followed by 4 bits at 125 nanoseconds. And if we look here, we've got an FC. That's 1, 2, 3, 4, 5, 6 high bits, followed by a bunch of 0 low bits. There's 16 bits here, but we're only going to use the first 10 because we configured the SPI only to send 10. On the flip side, when we go back here and we say, for a low, we want 3 bits low, followed by 7 bits high. If we look at an E, that's 1, 1, 1, followed by a whole bunch of zeros here. So we've got our SPI 1 and SPI 0 values. I created a DMA buffer. Essentially, we're going to build all of the bits that we want to send out to the LED in a buffer. Is 5,000 enough? Really should probably make that something that's specific. We've got number of LEDs down here. Let's move that up to the top. We know we need 24 bits that we're going to send out per LED. So this array is where we're going to put all of the data that we want to send out to all 60 of our LEDs. The DMA queue position is when we go to put data into the DMA buffer, where is our latest location? I created 2 functions, Q1-bit and Q0-bit, that let us put a 0 or a 1 into the DMA buffer. So you can pass it a parameter and it puts that many in. It turns out I designed this first. It turns out the only value I ever use there is 1 bit at a time. We want to queue up an RGB value for each of the 60 LEDs that we have. In order to do that, we get the R value, the G value, and the B and put them into bytes. Then we're going to walk through each of these bytes, queuing up the bits that we want to send to the array. Note that the order that we send them are G, R, and B. That's a peculiarity of the hardware. You can see we use a bit mask where we walk through that, checking each bit to see should we queue a 0 or a 1. Finally, we need to be able to send a reset signal. Oh, and we need to add a provision for that in the array that we create up here. We need to send at least 50 microseconds worth of lows in order to get a reset. We've got 10 bits at 125. (125 nanoseconds) times 10 bits per queue entry. And we're going to send out 80 of those. That gives us double what we need, 100 microseconds worth of delay. So we'll come through here. That'll let us queue up what we need to do. Finally, we'll need a way to start the DMA. And this is a little bit hardware heavy. You need to read the family resource guide for the PIC24 to understand exactly how all of this works. The important thing is that we're going to disable the channel. We're going to set the count to the number of words that we want to move out. We're going to set the destination to the SPI buffer. That's where the data that we copy is going to go. we're going to set the source to the beginning of our DMA buffer. We're going to set this guy up for a single fire on each time that the interrupt for the SPI goes off. These guys were things that were set up by the microchip code configurator. I just copied them in. And then we're going to enable this byte. So immediately this will feed a byte into the SPI and continue feeding bytes until we've moved this many. It'll only feed bytes when the SPI says it's ready. That's why this is set up the way it is to trigger on that particular channel. So we have this function that gets called periodically from main, the update. So we're going to send out the data for however many LEDs we have. We're going to iterate through them from 0 to the number of LEDs. And I've got some code in here I was working with before. We'll take that out for the moment. If the current LED is what we're calling the chase LED, then we're going to put a color on that LED. Otherwise, we're going to send it a 0 that'll shut it off. So at any one time, only one of the 60 LEDs is going to be turned on. We send the reset signal after we've sent data to all of the LEDs. Then we kick off the DMA. The DMA will actually do the streaming into the SPI to send all of those. Now I'm going to put just a busy wait in here that will eat up some period of time, longer than what it takes to clock them out, actually significantly longer, so that we as humans can actually see the LED moving down the strip. Once the delay is over, we're going to say, okay, let's set up and let's move the LED forward one on the strip, the lit LED forward one on the strip. And if we get to the end of the strip, let's set the LED back to the beginning. Let's increment the color. If we're up to the top of this color table that we set, then let's go back to the beginning. So let's run this code and take a look and see what it looks like. You can see we're getting a little complaint there that in our DMA code, we're using a pointer as an integer. We're feeding the value into the output. I'm sorry, we're feeding that value into a register. Now let's take a look at the oscilloscope again and see what we're getting. What we can see here is that we're getting a whole bunch of bits in a row. The DMA is effectively keeping the SPI fully loaded so that every word, one after another, is getting loaded into there. This is much faster than we could do it if we were doing it just using the CPU to manually go into a loop and load the values. So each of these guys, you can see it. These are the data that's actually coming out of the SDO. This is just our reference clock showing how long each of these bytes is taking. Now let's take a look and see how it works. We can see that our light is moving along the track. We're seeing a current pull of around 60 milliamps at 5 volts. Now, one of the questions we had before is how much current does the WS2812B pull? So we're going to modify our code a little bit. We will take out the part of the code that does the LED chase. And if I is greater than some number, we'll say 10, I'm sorry, I is less than 10, we will turn on the LED with some color. Let's start with red. Otherwise, we will turn the LED off. Now what we can see here is that we've got 10 LEDs turned totally on, and we're pulling about 1.6 milliamps. I'm sorry, 160 milliamps. So approximately 16 milliamps per LED. Let's go ahead and bump that up to 20 and see what that does. 2.8. Let's go up to 30. 4 amps. And a single, let's go down to 1. You can just barely see it back there in the background. 52 milliamps. So one of the good questions is how much current does this strip of 60 LEDs pull when it's not turned on at all? And this ammeter is set up only on the 5 volt in to the strip of LEDs. So 40 milliamps for 60, so about 2/3 of a milliamp per LED, even when they're in the off position. Let's turn all 60 of them on. About 0.75 amps. And you'll note that my supply voltage, which I'm measuring at the LEDs, has dropped to 4.5. So I'm getting a significant amount, about a half a volt of drop through the various cables that I'm using up to the LED supply. What that tells us is that in our design, we're going to have to be careful because we're going to be pulling a significant amount of current. And so we don't want to use a lot of thin, long wires. We want to keep things tight and well supplied. Let's go ahead from the reds. Let's take a look and see what green looks like. There's our value for green, and we notice that the current didn't almost drop at all. So on average, these LEDs are pretty common with their current regulation. Let's go ahead and run the tests for 1, 10, 20, and 30. Now let's go back to blue. Okay, now let's take a look and see what happens when we turn on all 3 color segments and get a white output. At 60 amps, at 30 LEDs, we saw 1.1 amps. At 60 LEDs, we see 2.1, so a little less than double. One of the things we see here is that at this point, we're getting a significant amount of drop in voltage coming into the LEDs. If I take a look at my voltage regulated power supply, it still is providing 5 volts at its terminals. So all of this loss is happening through the various connectors that I have through the multimeters and things like that. So this definitely shows that the quality of the connection between our power supply and the LED chain is a critical design aspect of this particular project. From the data we just took, we can tell that there's a very strong linear relationship between the number of LEDs and the current draw. The green, blue, and red lines are virtually on top of each other. The R-squared is very, very strong. So we saw that for 60 LEDs at 0 current, we had about 40 milliamps of draw. So it seems reasonable to think that this WS2812B will draw about 600 microamps per LED, even when the lights are off. Additionally, for each color turned on at 100%, you can expect to draw about another 12 milliamps. So we would expect to see at white about 36 milliamps per LED turned fully on, assuming that the LEDs are being run within their expected voltage range. Let's take a look real quick at how the system does regulating on the PWMs. Let's go back down to 10 LEDs. 400 milliamps. Now let's cut that PWM in half. 220. And as we remember, there was a significant amount of pull with 0 power on the LEDs. So it looks like there's probably a reasonable MX plus B offset. Let's go ahead and get one more data point on there so that we can take a look at the linearity. Finally, let's go ahead and turn all of these guys on and take a look we'll turn on 10 LEDs full power, and we'll take a look at how it regulates current as voltage varies. Note that for an LED, it's the current running through it, not the voltage across it, as long as you get beyond a certain point that determines how bright it is. So here we can see 10 LEDs that we're running at full power. I'm going to turn down the voltage supply on this and watch the guy on the left go. Down to 4.5. We see it's pretty stable down to 3.7, 3.5. Then we start getting rapid drop off around 3.3. And we can noticeably see a dimming of the lights. So at 5 volts input, we're seeing 400 milliamps. At 4 volts input, we're seeing 380 milliamps. So we had a 20% drop off in voltage, but we saw a 5% drop off in current. So the current regulation relative to voltage seems relatively good on these chips. As we turn this back and forth between 5 and 4, I'm not seeing any visible change in the LED brightness. Note that at one point I overshot and went too high and the LEDs turned off. I don't know if that's a protection feature or a malfunction at the higher voltage, but that just happened. From this exercise, we learned 4 things. Number 1, we could definitely drive the WS2812B from our PIC 24FJ26GA702. Second, the power line length and capacity is relevant when all the LEDs are on, so we'll have to design around that. Third, the WS2812 pulls about 600 microamps when it's idle. And fourth, each color pulls about 12 milliamps at full power at 5 volts. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting.